Welcome to the deep dive. Today we're venturing into a really fascinating cosmic puzzle. We're connecting the sun's powerful activity, the subtle dance of the planets.
And the mystery of dark matter.
Exactly. You, our listener, showed interest in these areas that seem, well, pretty separate.
Right.
So our mission today is to explore these potential links, make it insightful, but hopefully not leave you feeling totally lost in space.
Absolutely. We're tackling a really fundamental question about our own star, the sun.
Its activity cycle.
Yeah, that roughly 11-year cycle. We've got a couple of main ideas about what drives it.
Like what?
Well, maybe it's a turbulent dynamo effect,
Hmm.
something churning inside its outer layers.
Okay.
Or maybe it's more about these large-scale wobbles, oscillations
Huh?
of a really old magnetic field deep inside, a fossil field.
Right, buried in the core. But the exact details.
Still fuzzy. Things like how sunspot numbers vary exactly, or those really quiet periods like the Maunder minimum.
We don't have the full picture.
Not completely, no.
Yeah. Okay, let's unpack that. We've got this regular rhythm in the sun's behavior, but the engine driving it isn't totally clear.
Precisely.
But here's where it gets, well, really interesting, I think. For over centuries, scientists have noticed these hints, intriguing hints.
That solar activity might be tied to the sun's own movement.
Yeah, as it orbits the center of mass of the whole solar system.
It's a subtle wobble, but yeah. And what's fascinating is the sheer range of things that seem to correlate with that motion.
Especially its acceleration, right?
Exactly, the changes in its acceleration. Since the 1960s, people have pointed out potential links.
To what kind of things?
Oh, everything from the basic sunspot counts.
The wolf numbers.
Yeah, those. But also longer-term climate shifts here on Earth.
Wow. Okay.
And those longer cycles, the Gleisberg cycles, about 80 to 90 years. Even those big quiet spells, like the Maunder minimum we mentioned.
So it's not just one thing.
No, the variety is what keeps this idea alive. You
Yeah.
know, this planetary influence idea. It's persistent, even with the skepticism.
And the list, I mean, it just keeps going.
It really does.
We're talking short-term blips in the sun's brightness,
Luminosity variations, yeah.
the peaks and troughs of the sunspot cycles, a huge, 2,400-year cycle they see in tree rings using carbon-14.
Right, the C14 acts as a proxy for past solar activity.
And even differences between the sun's top and bottom halves, hemispheric asymmetry.
Yep, that too. And how sunspots cluster over long time scales.
Okay, wait, there's more.
Oh, yeah. There are times when a certain rule about sunspot behavior, the Nevichev-Ol rule, seems to be violated.
Huh.
And correlations with certain isotopes, the cosmogenic radionuclides.
Created by cosmic rays.
Exactly. Looking back almost 10,000 years with those.
10,000 years.
And then there's the total energy output, the total solar irradiance, or TSI, that we've measured since '78. Variations there, too.
Right.
Plus, some really strong cycles they see in radio waves from the sun that seem to match planetary periods.
It's a lot. I even saw mentions, kind of weird ones, about links to dust storms on Mars.
I've seen those papers.
And river flows on Earth. It really makes you wonder if everything's connected.
It certainly, well, raises an eyebrow. And you're right, that's where the scientific caution comes in.
Because
Well, while some peaks in these different data sets seem to line up nicely.
others just don't.
Exactly. So it leads to debate. Is it a real physical link? Or just, statistical noise? Finding patterns where there aren't any.
The correlation versus causation problem.
Precisely. And the huge stumbling block, the really crucial part, is we lack a known physical mechanism.
Right. How could the planet's gravity, which is pretty weak compared to the sun itself,
How could that gentle tug cause such big, varied effects on a giant star?
that's the fundamental sticking point.
It really is.
Okay, so it's like the ice cream sales and shark attacks thing.
Kind of, yeah. You see a correlation, but it doesn't mean one causes the other. There might be a hidden factor or it might be chance.
But within all this, there's a specific kind of unusual part of the sun's movement people have focused on.
The retrograde motion.
Yeah, backward motion around the solar system's center of mass. It happened around 1990.
And earlier, too, like 1811, 1632.
Right. For a short time, its angular momentum relative to that balance point was actually negative. It was going the wrong way, so to speak.
Which is weird to think about for the sun. And it raises this question. Could that specific motion somehow link up with the sun's own spin?
How?
Well, people have tried to model it. Maybe tidal forces from the planets play a role then.
Uh-huh.
Or maybe it affects the tachocline.
Remind me what that is.
That's a transition zone deep inside the sun, sort of between the radiative interior that rotates like a solid body and the outer convective zone that spins differently, like a shear layer.
Okay, like gears grinding.
Sort of. The idea is maybe this backward orbital wobble could somehow stir things up there, in that sensitive region.
Has that idea gained traction?
Not really widespread acceptance. These mechanisms are still debated, contested. The physical picture connecting the sun's orbit to its rotation is, well, it's murky.
So let's recap. We don't have the full theory for the sun cycle,
Nope.
but we keep seeing these hints, these persistent correlations with planetary movements.
Right, even though we can't quite explain how it would work.
Now, here's an interesting thought. Sometimes in science, even if you don't get the why immediately,
You still need to test the if.
exactly, you test rigorously if the correlation is real, regardless of whether you have a neat theory for it yet.
That's a really crucial point in the scientific method. And following that idea, a few years back, a proposal was made
To do what?
to test this whole planetary influence idea, but in other star systems. Look at exoplanets.
Ah, okay. How would that work?
The logic is find stars that get tugged around a lot more by their planets than our sun does.
Stars with big planets or close-in planets?
Yeah, systems where the star's acceleration changes significantly because of its planets. If planetary motion does influence stellar activity.
Then you should see stronger effects or clearer patterns in those systems.
Exactly. They pointed to systems like HD 168443 and HD 74156. The orbital momentum changes for those stars are huge, like orders of magnitude bigger than the sun's.
So prime candidates for seeing an effect, if it exists.
Definitely. But as far as I know, those specific tests haven't actually been carried out yet.
Huh. So the idea is out there, but not yet tested.
Seems so. But the fact these correlations keep showing up for our sun makes people wonder, can we find similar stuff elsewhere? It might give us clues.
Okay, so looking at exoplanets is one path forward, but now the story takes a pretty unexpected turn.
Right.
In late 2019, we heard from Konstantin Ziotas, a researcher at CERN.
Mm-hmm.
He wanted our take on a paper he'd co-authored, and the title was something like The Sun and Its Planets as Detectors for Invisible Matter.
Yeah, that definitely makes you pause. Invisible matter. Dark matter.
So shifting gears quite a bit here.
Absolutely. This connects solar flares, the big ones, M-class and X-class flares, with the positions of Mercury, Venus, and even our moon, over decades of data.
Okay, connecting flares to inner planet positions. But where does dark matter come in?
Well, dark matter is, as you know, maybe the biggest puzzle in physics right now.
We know it's there from gravity.
Right, it's gravitational effects on galaxies, galaxy clusters, loads of evidence on large scale.
We haven't actually detected the particles themselves?
Nope. No convincing direct detection yet.
And we usually think of it as this big, smooth halo around the galaxy.
Mostly, yeah. But there's also evidence for, streams of stars in the outer galaxy.
Leftovers from smaller galaxies the Milky Way ate.
Exactly. Cannibalized dwarf galaxies. And the thinking is they probably brought their own dark matter along with their stars. So maybe the dark matter isn't perfectly smooth. Maybe there are streams of it, too.
Okay, so streams of dark matter possibly flying through the galaxy.
That's the background. Now, Ziotas and his colleagues had this really interesting hypothesis.
Which was?
They suggested that for certain types of dark matter particles, moving at specific, very slow speeds, like 110,000th the speed of light, planets could act like gravitational lenses.
Focusing them, like a light.
Kind of, yeah. The planet's gravity could bend the path of these dark matter particles and focus them towards the sun.
Okay.
And if these dark matter streams aren't random, if they come from preferred directions in space,
then you'd expect more focused dark matter hitting the sun when planets are in certain spots.
Precisely. And if that influx triggers solar activity,
you'd see more flares when planets are in those focusing positions.
That's the core idea.
And they focused on Mercury and Venus.
Yeah, presumably because they orbit quickly compared to the 11-year solar cycle, so you get lots of alignments to check over time.
Makes sense. And what did they actually find in the data?
Looking back in 1976 over 4 solar cycles, they found a statistically significant bump in those big M and X flares when Mercury, or Venus, or both, were in a specific slice of the sky, as seen from the sun.
A specific direction?
Yeah, when their heliocentric longitude was between roughly 230 and 300 degrees.
Heliocentric longitude? That's like the planet's address in its orbit around the sun.
Exactly. It pinpoints its location relative to the sun and a fixed direction in space.
So the bottom line of their hypothesis is big solar flares might be triggered by dark matter streams.
Coming from a preferred direction.
And planets act as lenses to focus it onto the sun.
That's the proposal. It's definitely out there.
It's pretty radical. It connects solar physics, planetary science, and fundamental particle
It
physics.
really does. And thinking about this, uh, two potential ways to test it further were suggested.
Okay, how could we test this idea?
Well, first, go back to exoplanets. Look at other stars with planets.
Right.
If this dark matter stream idea is real, and if it's, say, related to the galaxy's structure, like infall from a certain direction.
Then that direction should be the same for other stars, too.
Exactly. So you'd look for increased flare activity in other planetary systems when their planets align along that same direction in galactic space, the same galactocentric longitude.
Ah, I see. So the special direction shouldn't just be special for our sun, but for any star in that stream's path.
Precisely. It tests if the phenomenon is local or galactic.
Okay, that's one test. What was the second?
The second uses data from the Gaia mission
Which is mapping billions of stars' positions and motions.
in incredible detail.
Hmm.
The idea here connects back to those stellar streams we mentioned, the remnants of consumed galaxies.
Uh-huh.
If solar activity reveals dark matter falling in along the path of an ancient stellar stream,
Then maybe the stars from that same stream are also still moving along that path.
right? So you look in the Gaia data for ancient stars, ones with low metallicity, that show correlated motions moving together through space along the same path as this hypothesized dark matter flow.
So you're looking for the stars that were the fellow travelers of the dark matter, remnants of the same galactic merger event.
Exactly. The assumption is that the stars and the dark matter from the captured galaxy might still share similar orbits or trajectories within the Milky Way.
That's clever. Using the stars as tracers for the dark matter path.
It's an interesting approach. Now, obviously, tackling this needs expertise across, well, quite different fields.
Dark matter physics on one hand, stellar halo dynamics on the other.
Yeah, not disciplines that always talk to each other directly. It takes a broad perspective.
Which is why the next logical step was to, share the problem and these test ideas.
Right, send the outline to colleagues who do work in those specific areas,
Yeah.
get their feedback, see if the tests are feasible, if the idea holds water from their perspectives.
It really shows how science works. Sometimes collaboration is key when you hit these big interdisciplinary questions.
Definitely. And there's actually a little postscript to this whole planetary influence part. A
Oh,
more recent study, I think by Edmonds in 2022, suggested that if you include the hypothetical planet 9 in the calculations for the sun's motion around the solar system's barycenter,
the center of mass, yeah.
the correlation between that motion and the sun's activity cycles actually gets better.
No way. So even the standard planetary mechanics angle might still have some surprises, maybe involving planets we haven't even confirmed yet.
Could be. Just adds another layer to the puzzle.
Wow. So wrapping this up, we've really journeyed through quite a landscape today.
We definitely have. From the sun's basic activity cycle mystery,
To those long-standing, perplexing hints of planetary influence.
right, the correlations that won't quite go away, even without a clear mechanism.
And then leaping into this really speculative but intriguing territory where dark matter might be playing a role.
Yeah, potentially triggering solar flares via gravitational lensing by planets.
It really hammers home how things we think of as separate solar physics, planetary orbits, the nature of dark matter might actually be interconnected in ways we haven't fully appreciated.
Absolutely. And it highlights how sometimes ideas that seem, a bit fringe at first.
Can actually push us to ask new questions and maybe lead to important insights down the line.
It keeps things interesting, that's for sure.
So here's a final thought for you, the listener, to mull over.
Mm-hmm.
Given that these seemingly distant things, the mechanics of planets orbiting, the invisible substance making up most of the universe's mass, might be subtly influencing our own sun's behavior,
Yeah.
what other hidden connections might we be missing? What other unexpected links could be shaping our cosmos and our place in it that we just haven't stumbled upon yet?
It's a great question. It reminds us that there are probably still plenty of surprises waiting out there, especially at the intersections of different scientific fields.